So my name is Adam Leśnikowski, and as Adam said, I'm a machine learning scientist at Nvidia. I've been there for about 2 years now. And I'd like to tell you about some of the work that we've been doing on active learning, machine learning, and applying these to some of the deep neural networks that we use for our autonomous vehicle program. So the talk of this title is Data-Driven Dataset Creation, Deep Active Learning for Autonomous Vehicles and Beyond. And I'm excited to talk to you about some of the work we did. And so just by show of hands, I'm curious, by way of background for this talk, who's undergraduate? Who's like at master's level? Cool. Who's PhD? Okay, and postdoc? Okay, faculty? Industry? And other? Okay, I guess others. We can talk later. Curious what you're doing. Okay, great. So I'll try to gauge the talk and calibrate the talk based on that. So in this talk, we'll see how we used and developed active learning with a particular emphasis on the autonomous vehicle use case. So in Nvidia, we're building a self-driving car, so everything from the hardware up to the software stack. And so why do we need to care about, first of all, by way of motivation, why do we need to care about a data set creation, especially data-driven data set creation? Well, the motivation is, so maybe you could think that, can't we just brute force everything? Can't we just label everything? Don't we live in the age of AI? We can just, label everything and have AI figure it out? I would argue no. And the biggest reason is that we have a lot of data, and we can't possibly label all of it. So we're not there yet. We're not in an age of fully automated data set creation. So I think some of the motivations, why I don't think we should or can try to brute force everything, I think there's better ways available. So why are we doing what we're doing? So first of all, cars, so we have a fleet of cars, and cameras, they give us data, so lots and lots and lots of data. Think like petabytes per month. So we have a lot of data. And we also know from kind of machine learning the last few decades, and especially deep learning the last decade or two, that if you have enough labeled data on the lower left, together with state-of-the-art neural network models, we can basically just have self-driving cars, or at least we have the networks for the self-driving cars. And I guess there's Angry Birds here, but if you were to update it today, I don't know what you play. I guess Fortnite or Dota, or I guess Dota is almost even solved, right? We'd be training your RL agents to play Dota. So you can do whatever you want. You can read a book. But we're not there yet. So the biggest question for us is how do we get from the upper right here, so vast amounts of unlabeled data, to the labeled data that we need in order to play Angry Birds or Dota. Okay, and kind of in industry especially, we like to think in terms of time and money, and that's obviously true, but we want to really reduce these. We want to be able to turn a profit from what we do. And moreover, so it's not just the limited amounts of label compared to the budget we have. Not all data are created equally. So we have really a lot of these kind of miles, so these are boring highway miles. And we also have just things which we don't really expect to find. And things that are really going to drive the hard cases for autonomous vehicles. So these are the sorts of things that we want to find, and we want to be able to find them without actually knowing the categories. So we want something that automatically, in an automated way, discovers new kind of unknowns. And we want to label those, and we want to put them in our training sets so that we can improve performance on them. So some samples are much more informative than others, and I'll have results that point this out in a more quantitative way. So how do we find the most informative unlabeled images so we get the safest autonomous vehicles possible? And how do we improve the sample complexity of our training? So these are the two big motivating challenges for us. Okay, so let's take a look at traditional machine learning. So I'm curious, who has a background here in machine learning, just by show of hands? Okay, great. So in traditional machine learning, the approach is we have some train set, we have some model, and the model is optimized on the train set, and the train set is fixed. And just by way of the last talk before me, which was excellent, so at the end there was this idea of either active learning or active machine learning, and this is the exact approach that we take. So in industry, we actually have this unlabeled pool of data, and we have the resources, and really the power and the luxury in order to be able to create this train set here on the left. So in particular, our approach is to take our unlabeled data and incorporate feedback from our model in order to decide what to label. Okay, so we're recruiting our model in order to basically tell us, among other things, which samples it finds hardest in order to improve the sample efficiency and also find hard examples. Okay, so it's an iterative process between going from the model, training it, and then looking at unlabeled data. So the process iterates between model training and labeling data. So once we have these kind of most confusing or most informative examples, we send that to labeling and then add it to the train set. And this whole loop we call the active learning loop. And in this particular case where we use natural images, the pool-based active learning loop. Okay, so this is the approach that we have. Okay, so next I want to go to some results. So here's the setup classification. I think it's all pretty clear for this audience. We want to be able to classify into one of n categories. So we actually did it on some classification tasks, but also we have some results on tasks that we care about. So we have a lane segmentation data set. So for our experiments, we used about 100K train, 10K test split. And the idea is we have binary classification for lane markings. And one of the challenges of this data set is a heavy class imbalance. So most things are non-lane markings, and relatively few percentage are lane markings. And this is useful for all kinds of things, like keeping your car on the lane so you don't swerve off. So we also have slightly harder, which is object detection. So we want to be able to detect things like cars and pedestrians and avoid them, not hit them. Okay? And again, the data set is roughly 100K. In this case, it's a little bigger with a 10K test split. So on segmentation, we started this project and we said, how well can we do using this kind of active approach where we iteratively build the data set together with model training? And here's a result from last year where we have, so on the right is all the data. So we get about almost 0.76. So this is F-score. If you don't know what it is, it's not super important, but just think of it as a metric you want to optimize. So higher is better. And on the left is an active learning setup where we initially train the model with 30% random data and then augment with 30% more data that's selected by the model. So in particular, it's selected by most confusing as measured by image entropy. I can show you some examples of what I mean by that. And so how do we do? Okay, well, we do much better. So this is almost 0.79. So we get a real big performance gain just from one loop of this active learning cycle, which is great. Okay, and here's a robustness analysis. So we can do this same experiment about, in this case, we did it 10 times. And on the right is a box plot of 10 runs of using basically baseline, so random sampling strategy. And on the left is this same setup where we take 30% and add 30% more using an active setup. Okay, so really this result is repeatable. So that's great. And it's especially important because if you think in the active learning cycle, you don't get a chance to do it again. Like once you've already paid the cost, you can't go back and unpay that cost. So you want to get it right the first time. So in particular, for a lot of machine learning and deep learning applications today, which are very exciting, I would advise you to take a cautious look at how much hyperparameter tuning is needed. And in some cases, that's fine. Maybe you have a lot of compute. But in some cases, you really need to get it right the first time. So especially safety-critical applications at test time, like you can't, for instance, you can't undo mistakes that you do, say, in autonomous vehicles or medical contexts. And in our context, active learning, you pay the cost. You can't go back and unpay it. Okay, and so just to give you some intuition about what this network is selecting. So on the right are low entropy images. So just as an aside on this research, the approach that we actually used and we piloted was just a baseline that we implemented. It worked so well that we didn't decide to do some of the other results. So sometimes strong baselines work relatively well. That's, I guess, one lesson I want to stress from industry. So on the upper right here, 2 low entropy images. And they're low entropy because almost all pixels are either confidently predicted as either background, so dark purple, or as lane markings, dark yellow. And on the upper left are high entropy images, so there's more shadings of intermediate colors like green and blues over here. Okay, so this is just the intuition of what kind of labeled images, or sorry, what kind of images the active learning loop is selecting. And these are predictions of the model on the upper left, on the upper row. Okay, so we also have some results on detection. So the detection experiment setup, again, was about 100K trained images, 10K test images. And how do we do? So here's object detection performance, where MAP, so again, it's a metric. If you're familiar, it's mean average precision. It's a very commonly used precision metric or performance metric for object detectors. And does anyone know what MAP is, just out of curiosity? What is MAP? Maybe does someone want to say? What's MAP? Mm-hmm.
So it's like you measure how good your bounding box is fitting different two bounding blocks, and at the same time you are taking a mean on classes.
Yeah, so it's mean across average precisions of the classes, and average precision, one way to think of it is as you vary your threshold confidences, it's the precision across those threshold confidences. Okay, so in blue is our baseline. So here's our performance of our model using just some random data. This is the base model, so this is before kind of the A-B split between random sampling strategy and the active sampling strategy. The random strategy is going to be in purple, and the active strategy is in orange. So next slide, we get a really nice performance gain in the orange versus the purple. So in this case, purple gives us almost no data. And that's another trend that we saw, that in many cases, additional data provides you almost very little. And it's quite interesting, I guess, from a learning theory perspective of why some images have just much more information after you train a model. Okay, and here's actually, so this is object detection across all categories. Here's object detection for a particular category that we want to improve on. So this is persons, and as a pedestrian, I'm quite happy that we're able to get this performance gain. So again, blue is the baseline before the A/B test. Purple is the random baseline strategy, and orange is the active strategy. So that's great. So we really have a big performance gain based on the active strategy. Okay, and just to give you some more intuition as to what's happening here, so if you take all the images in our unlabeled pool and you sort them by our confidence metric, then on top is the image, so the one image from our data set where it has lowest uncertainty. So this is intuitively the thing that we should label with least priority because the model is quite certain on it. And you might be curious what these two images are doing. Well, our uncertainty metric, so it's basically a disagreement of an ensemble. So what we did is we trained n models. In the easiest case, it's just 2 models. And then the uncertainty metric is, well, how confusing is the image to the ensemble as measured by the disagreement between predictions. So you have, say, 2 models. You predict on unlabeled images, and the level of disagreement is the measure of confusion. Okay? So if the 2 models are predicting things exactly the same, that's going to be lowest confusion. And keep in mind that this is on unlabeled data, so we have no ground truth. This is, we're trying to predict stuff without actually having labels. And on the bottom is the most confused images, and this was, I want to stress, discovered in an unsupervised way. So here what we have is basically everything in autonomous vehicle background domain knowledge that we know is difficult. So we have nighttime scenes with pedestrians with like a big truck in the background. So that was really great to see as a sanity check. Okay, so the next line of work that we did was, this was actually, we presented at the NeurIPS conference earlier this month, so last week. So this was, we proposed basically a hybrid architecture of a Bayesian and deterministic network. And you might be wondering what's Bayesian networks doing here, or even what is a Bayesian network? Well, put simply, a Bayesian network is where you put a distribution over your weights instead of a point weight. Okay, so the idea is that it does a better job of capturing uncertainty than just a deterministic network. And the connection with the previous work is that, notice that the active learning metrics are metrics of uncertainty. So things that are more uncertain get sampled, labeled with higher frequency. And so we really were motivated by getting better uncertainty metrics for our models. And the best approaches that we found were these Bayesian methods. And there's a lot of interesting work and a lot of research that's happening now in Bayesian deep learning. and we wanted to kind of tap into that and move the field forward. So we proposed this hybrid architecture. And the reason it's hybrid is because if you go fully Bayesian, then that's great. You get like the best uncertainty estimates. But in terms of memory and compute, it's the most, it has the highest footprint. So you have at least 2 times as many parameters to keep track of. If you parameterize by, say, a Gaussian, you have both the mean and the standard deviation, so the sigma and the mu, and that's at least 2 times as many parameters, and everything is just going to get slowed down. So in terms of memory and computation, it's not so great. So we said, well, what if some of the layers are actually deterministic and the other ones are Bayesian? Can we still get the uncertainty estimates that we want? And it turns out the answer is, well, I'm presenting it so we can. Otherwise, this would be pointless. I wouldn't be presenting it. First of all, we had some examples, and this actually was incorporated into the official TensorFlow probability repository. So if you're familiar with probabilistic programming languages, PPLs, basically Edward was one of these, probably one of the most well-known ones. It got merged into TensorFlow, and now it's called TensorFlow probability. So we were quite happy to see this merged. And so first of all, we have kind of a tutorial to show how you can train, and in particular, how you can extract uncertainties. So I point your attention to this upper right, where this kind of ambiguous image has a posterior distribution that's between at least 2 categories. So that was kind of a nice sanity check to see. Here's some training graphs. And kind of the big takeaway for us is that they do take longer to train. But it turns out that most of the layers don't need to be Bayesian. So in particular, if you have, say, 10 layers in a deep neural network, we found that we can get good uncertainty estimates with only just the last few layers being Bayesian and everything else being deterministic.
So how
Yeah,
do you
question?
train them? Do you train them deterministically first and then train some of the layers in this Bayesian fashion? Or?
So we train them in just one go.
Okay.
And in the package that we used, it's possible to have a mix of Bayesian and deterministic layers. So, yeah, question?
I bet you use the package uses the parameterization trick to parameterize to just push the stochasticity outside of the computing graph so it can go with the gradient, right?
I believe so, yeah. I believe so.
And do you use any other distributions than Gaussian?
So it's all Gaussian. So in this case, it's all Gaussian. Exact. So that's a great question. It's a limitation of this work that we want to explore is maybe it turns out down the road that there's some other great class of functions where you want to put as your posteriors for the weights. We didn't explore that. We did explore different parameterizations of the Gaussian. So you can actually tune how Bayesian the network is by setting both the initial width of the Gaussian together with like the max width. And these are kind of continuous levers that you can turn of how Bayesian or Gaussian it is, and we have some results there in the paper as well. So I'd encourage you to take a look. So this is done by one of the interns who worked with us, Xiaoming Zheng. And it turns out it works, and most of the layers can be deterministic. So that was great to see. So some other work that we presented last week as well at NeurIPS was this probabilistic ensembles for segmentation. So again, this is motivated by the need to get really good uncertainty estimates for this active learning cycle. And I would say also, why care about kind of these uncertainty estimates? So active learning is one big application, but also if you're driving a car or say doing a diagnosis, uncertainty information is really important. So think of the difference between, say, predicting there's no cars and being absolutely certain about it or very certain, and predicting there's no cars and like, who knows? Maybe it's like a foggy image. That's going to lead to a huge difference in terms of how your car is going to behave. Or think in the medical case where doctors, they kind of hedge their bets and they give you some good uncertainty estimation. They say, it could be pneumonia, but it could be something else, and we're not really certain. Or like it's pneumonia, and like take this medicine right now. So we want to be able to have that kind of uncertainty estimation in our networks. So what we did was we proposed this new kind of architecture which takes a regularization, so technical terms, it takes a regularization that's inspired from looking at the evidential lower bound loss. So the evidential lower bound in kind of the Bayesian world is this mix of both the negative log likelihood and another term, and then we took that other term and used it as a regularizer. So it's a KL divergence regularizer. And we got some state-of-the-art results on the segmentation results. So in particular, there's this Berkeley Deep Drive data set. So it's 100K. It came out from the Berkeley Deep Drive Collaborative at the beginning of this year, and it's the largest kind of open source data set for autonomous vehicles. And we're super excited to see it got great results on that, and also some state-of-the-art active learning results on basically benchmark data sets like CFAR10 and CFAR100. Okay, and then basically the setup is we pre-train on cityscapes, so this idea of transfer learning, which from the last talk, I totally agree, it's a great idea. So it's another autonomous vehicle data set you can pre-train, and then we evaluate active learning on this Berkeley Deep Drive 100K. So any questions so far? Did I go too fast or too slow? Okay, cool. So here's the setup, evaluate active learning on Berkeley Deep Drive 100K. And in particular, we really want to make this kind of some feedback from how humans label things. It's really impractical to have them label this whole thing. And just in terms of cost, so as a machine learning practitioner, you might get these data sets, but they cost a lot of money to make. So for autonomous vehicles, to get just the object bounding boxes, it costs something like $1 to $10 per an image. And multiply that by the millions of data points that you might need for an autonomous vehicle project, and these costs really start to add up. For semantic segmentation, it's more, it's like add another order of magnitude. And then I think there's really a lot of applications for these techniques in the medical context, where one of my colleagues works in medical imaging, and he says, you need really high-paid experts in order to be able to semantically segment, say, CT scans. And these experts, they don't come cheap. And also you need like 3 of them because there's a lot of interlabeler disagreement, so you want to have an ensemble. And so the cost is something like 1,000 to 10,000 USD. So it's almost, it's impractical just to label a huge amount of things. And we have a lot of great graphs and results. And in particular, I want to point out that for hard classes like motorcycles, so with 32% of the data, we're able to get almost the same as much as adding all the data. So that was a really great thing to see. Some cases, here's a failure case, so bicycle actually did worse with the active learning. Sometimes it happens. You have this like limited amount of goodness. So we hypothesize that you have a limited amount of goodness that you can spread across the categories. And so orange is with active learning, and blue is if you just did it with all the data. So blue, think of it as an upper bound on your performance. Oh, sorry, you're right. You're absolutely right. So with bicycle, if you add all the data over a baseline, it does worse, which you might think is weird. And we thought it was weird, but actually we saw this with other experiments as well. So it turns out that if you train, so there's a common dogma, I think, in machine learning that just throw all the data at the problem into your model. If it has high enough capacity, it's going to learn. But actually, maybe your data is noisy, or maybe adding all the data introduces class imbalances that you may not want to have. So if you filter your data, so I actually talked to some of the autonomous vehicle teams, and they hand filter data based on, first of all, noisy images, and together with, they want to upsample rare things. So if you train with just that like filter data, you get better performance than you train on all the data. And so that's kind of the hand-ruled part. If you just did it with these rules that people know, we actually want to, if you take seriously this kind of data-driven approach, everything that you do by hand, we want to be able to do in an automated way. So it was really nice to see that in, at least for some of the categories. Okay, we also have some results that you can target classes. So what do I mean by that? Well, you can say, actually one of our colleagues said, on this graph, your performance is really good for some categories, but the stuff we care about, so they were basically detecting and classifying traffic signs and traffic lights. So the performance of active learning is actually worse than a random baseline. But what you can do is you can take the variance on just the output heads that predict those problematic categories. And we found really a significant performance gain. So if you take, for instance, foreground classes, so foreground classes are like motorcycle, bike, train, bus, truck, all the things you can hit in a car. And if you just take active learning based on the variance on those output heads, so like the variance based on those predictions, then you get a lot better performance than if you didn't, if you just did on all the categories. And in the bottom graph, which I'll let you parse offline just because it's kind of a busy graph, we did it for persons in particular. So persons did much better than the other two baselines. And yeah, so that's actually one side effect that we found, that so this graph, what I want to really make the point is that you can target particular classes, so you could just look at the variance of, say, foreground classes or persons, and you get better performance there, which is great. But also your point, which I didn't really say yet, but it's definitely there in the graph, that if you target, say, for instance, traffic signs, you get also better performance on things like walls and fences, so semantically similar categories, which is kind of interesting and kind of nice to see. It kind of makes sense. Yeah, so I would totally agree with that. So the point was, if you target on, say, foreground classes, the performance on the other categories does worse than kind of the original graphs, and that I think that's absolutely right.
So maybe like making bigger model would help?
Potentially. So one thing we didn't do, which I think might test that, is to look at the label distribution of the things that were requested. And if it's like, say, all like trucks and cars, then I wouldn't think that a higher performance model, higher capacity model might improve, but I mean, it's an experiment that's definitely worth doing. Cool, so I want to kind of do like a lightning round of, let's see how much time, okay. Maybe for the sake of time, I'll skip some of these. I'll do some of them like a lightning round style, really quick, just to give you some lessons that we found, and then I'll end there and then ask questions. Okay, so here's some classification results. So I think it's nice to see some of the kind of lessons that we found there that potentially lead to other experiments. So kind of the setup here is that we train one model here in green, and then here's the random baseline if we add more data. Okay, so this is x-axis is epochs, y-axis is performance. In this particular case, it's accuracy. So we get some improvement just by virtue of adding more data. So baseline is here. Performance with more data is there. What happens when we, say, do the active strategy? We get a lot better, so that's great. So that's as we should see. And we can actually see that we can do it over multiple active learning cycles, so the performance keeps improving, which is great. We can do it over many more, so here in this particular case, it's 6 active learning cycles. And every active learning cycle, here, and here, improves, but there's some saturation effects. So it seems to asymptote at the performance if you were to have all the data. You can vary the growth parameter, and these 3 colors are different growth parameters. So in this case, we had 33% more data. In this case, we had 10%. In this case, we add 100% of the data. And those are basically half orders of magnitude. So this is just really illustrating the point that unit performance gain goes as the log of the data set size, which is great to see. And you can repeat that experiment, and it keeps going modulo these saturation effects towards the top. So you can also, we did this interesting experiment where you can do the least certain images, so all the things that you're least uncertain images, so I guess most certain images. And the green is going to be the most uncertain, and the red is least uncertain. So you get essentially no performance gain. And you can do it again, and you can do it 6 times. And for us, this was really important in that these are all the things that once you see them, you can just essentially throw them away. You can either just like not upload them from your car, or you can delete them from your data set. So really, it's like there's no new information in these samples. And it's great that we can detect those without actually having to label them. And there's kind of an interesting problem or related problem in classical machine learning, which is the so-called core set selection problem. So the problem is you have some data set, you train your model. What's the minimal subset in that data set such that you can recover all the performance? And it turns out that you can do it sometimes with 50% of the data or 25% of the data or even like 10% of the data. I went to one talk in Silicon Valley where the Amazon people, oh, I probably shouldn't have said it was that company, but oh well. They said that they were able to get basically the same performance with something like 4 or 5% of the data. So everything else is just, you can just throw out. So that's super interesting. And we kind of look at this as a core set selection problem, but without actually having everything labeled. Okay, I'll skip this, but suffice to say, we did some more experiments, and we were happy with them. And things scale, so you can also do this on ImageNet. It doesn't work as well, and this is something that's already in the literature, but it does work a little bit. And one of the hypotheses is that the large number of categories in ImageNet somehow breaks all the methods that we have. So for large categories, this is still very much work in progress. Although with the Bayesian deep learning stuff we present at NeurIPS, we do have some results on ImageNet that have been state of the art. So maybe that's one approach. Okay, so in conclusion, deep active learning is super effective. Our methods have led to really important, significant efficiency gains, and there's a lot of exciting work in progress. And so I want to thank these people, so especially Xiaoming, Yusef Kashap from the summer, my collaborator Jose, Aisha, Tim and Evan from last year, Clement at Nvidia, and also Shalini and Steven at Nvidia as well. So also I want to say apply to Nvidia if you're interested. So we're always looking for student and postdoc interns to help run our experiments and design them and implement them. And also we have full-time positions in research, applied research, MLD, LCV, and lots of other exciting areas, including robotics. So you can follow up with me. Here's my Twitter handle, @Leśnikowski, or grab one of my business cards for me. And I think NVIDIA is a great place to work with. We're really just 10K people, so very small, but the amount of impact we have on machine learning and AI is really pretty impressive in a lot of different areas, self-driving cars, robotics, and I would say what I'm doing, which is kind of this really interesting area of it's goal-directed, so we know what the goal is for research, but it's also very, I would say, basic and fundamental. So I didn't really think this existed coming out from my grad programs, that you could do kind of basic fundamental research that's also goal-directed, but it does, and I'm doing it, so it's been very fulfilling so far. Cool, thanks.
Could I ask you for a round of applause for Adam?